Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the structural characteristics when we are implementing the equivalent lateral force or ELF method. Now, this video does not give all of the information about the equivalent lateral force method. It's quite extensive. To learn more about that on your own, I would suggest getting a copy of ASCE 7 and looking in chapter 12 specifically. This is just meant to give us kind of an overview and hit the highlights of how to get some key pieces of information to execute the first several steps of the ELF method. So let's go ahead and get started. First, I'm going to be referencing ASCE 722. Now, if you're still using ASCE 716 or even 710 or an older version, some of this is going to be the same. There's going to be a lot of it that is updated. There's been quite a few updates between ASCE 716 and ASCE 722. So please just be aware I'm using and referencing ASCE 722 here. So what we're going to be talking about here is what structural characteristics are we going to need to determine about the structure itself. And then we're also going to talk in this video about relating those structural characteristics to the site characteristics. And if you noticed, I had another brief kind of summary video on site characteristics as it pertains to the ELF method. So you should check that video out as well. So one of the first couple things you need to do is determine the earthquake importance factor I, or some references call it I sub E, and that's going to be based on the risk category of your building. So a risk category is basically going to be based on different occupancy requirements and uses of the building, as well as some other factors that are influencing how your structure should be defined. But there are 4 risk categories. And depending on what the structure is meant to be used for, you will find yourself in one of those 4 risk categories. So, for example, let's write this down now. Hopefully you're writing everything down, but we're definitely going to write this little table down. We have risk category. I'm going to abbreviate that RC. Okay. We have risk category 1, 2, 3, and 4. Okay. Now, as your risk category increases from 1 to 2 to 3 to 4, that usually indicates that your structure is more critical somehow. Okay. Maybe it has a lot more people in it, or maybe it's housing materials that are very sensitive. So, for example, most hospitals are going to fall within risk category 4 because those are emergency type of structures, okay? Most fire stations and police stations will also be in risk category 4 because those are where emergency responders work. And in the event of an earthquake, you need to have those structures designed more robustly, okay? So that would be, a more critical structure, all right? Storm shelters are usually going to be risk category 4 as well. Now, on the opposite end, risk category 1, okay, risk category 1 is kind of like a much lesser critical structure. So, for example, an old warehouse that is just housing old car parts, that's probably going to be risk category 1, or a shed of some sort, or a barn that just has old tools and farming equipment, that would be risk category 1, okay? Most structures that we deal with usually fall within risk category 2 or 3, okay? A lot of structures fall in RC2 or 3. So what are the importance factors for these risk categories? So I'm going to make another column here. Importance factor. Okay, the importance the factor for risk category 1 and 2 is 1.0. Okay, risk category 3 importance factor is 1.25, and risk category 4 importance factor is 1.5. All right, so as you see, the importance factor increases as the risk category goes up. So in the case of like a hospital, risk category 4, you're going to have an importance factor of 1.5, more important. Okay. The next thing we're going to determine is the structural system and its response modification factor, which we call R. And we're going to get this from table 12.2-1 of ASCE 7, okay? Now, this is a big table, so if you have your ASCE 7 with you, I would open that up. It's a big table. It's spread out over multiple pages. The leftmost column has a whole list of different structural systems, okay? For example, you might have a steel moment frame, a special steel moment frame, or a steel special concentrically braced frame, or an ordinary reinforced concrete moment frame. So those structural systems, several of them are in the leftmost column, okay? In one of the kind of center columns, you see the response modification factor, okay? And these are different values. Most of them are somewhere between 3 and 8, okay? 3, 4, 5, 6, 5.5, whatever, okay? In the ballpark of 3 to 8, most of them. And they basically, the response modification factor basically is a way to quantify the ductility of the structure, okay? So typically, if you have a structural system that is more ductile, you're going to have a higher response modification factor, maybe closer to 6, 7, 8. If you have a structural system that is less ductile, or designed to be less ductile, you might have a response modification factor of 3, 4, 5, okay? Now, I'm not going to get into the nitty-gritty details of selecting the appropriate structural system in this video. All I want to mention is once you have the structural system, go to this table and obtain the response modification factor. There are other important piece of information in this table as well. There's something called the overstrength factor. There's some height limitations, a lot of other good information in this table. But for the purposes of this video and this information, I'm just going to focus on determining the story forces, which really for now just deals with the response modification factor, okay? So we get that. The next thing we're going to do is we're going to compute the structure's fundamental period T from section 12.8. Now, most structures you will be able to use the approximate fundamental period T sub A to perform that calculation, okay? T sub A here. So again, if you have your ASCE 7, open up to section 12.8 and find where I am here. T sub A, and again, most structures you'll be able to use this relationship, is going to be equal to C sub T times H sub N raised to the X power, okay? Now, H sub N is the structural height. So that's going to be from the ground level to the top of the structural system, okay? Ground level to the top of the structural system. C sub T and X sub T are values determined from table 12.8.2. So let's write that down. We're going to say get C sub T and X from table 12.8-2 of ASCE 7, okay? So hopefully you're following along with me in your ASCE 7 reference, okay? The next thing we're going to do is something that we actually kind of talked about before in our site background video. We're going to use the ASCE hazard tool, okay? That's the online tool, produced and published by ASCE to determine the site information. And again, we talked about this in one of my other videos. In particular, what we want to do is get those site parameters and the response spectrum, okay? Now, when I say site parameters, I'm thinking of these spectral acceleration values and their modified forms. So that's like S1, SS, SMS, SDS, SM1, SD1, okay? And again, we talked about a lot of that in one of our other videos. But we also want to get this thing called a response spectrum. Now, what is a response spectrum? Well, a response spectrum is a graphical relationship between spectral acceleration, which we're calling SA, and period T, okay? Now, when you go to the ASCE hazard tool, and again, I would encourage you to maybe pause this video and just play around with it. Go online and just type in, search for ASCE hazard tool. It'll come up, and play around with it. But when you get the ASCE hazard tool displayed on your screen, there's going to be a few different options for response spectrum, okay? One of them is going to be what's called the multi-period response spectrum. So I'm going to go ahead and sketch a graph of generically what that would look like, okay? So the multi-period response spectrum is you're going to have spectral acceleration on the vertical axis and the period in seconds on the horizontal axis. Now, this multi-period response spectrum, okay? This is going to give you a plot that is going to look kind of like this. It's going to sharply come up, and then it's going to sail on down and kind of level off. Now, it's going to be connected by points, okay? So you're going to have, a point here. Oh, didn't mean to scroll there. Point here, here, and so on, okay? Let's see if I can count them all right. There's 22 points, by the way. 9, 10, 11, 12, 13, 15. I'm going to throw a few more, 16, 17, 18, 19, 20, something like that, okay? And these are at specific values, by the way. Again, I'm just sketching this really quickly. These are all at very specific values, and there's 22 points. So some people call this the 22-period response spectrum because the shape of this is defined by 22 different T values, different period values, okay? So you could have that. You could have an older version or a more historical version of this, which we sometimes call the 2-period response spectrum, which has the same axis labels. This is SA. This is T in seconds. Now, the 2-period response spectrum is like this. It's linear, and then it flattens out, and then you have these really two nonlinear segments here. I'm sorry, I drew that a little wrong. This is a little bit up here. The first value has an SA value, non-zero SA value. Okay, so something like that, all right? This first point here, color code here, is what's called T naught, okay? It's going to give you a period of what's called T naught. I'm going to define that here in a second. And then the second flat line period here is going to give you a period called T sub S. And then you're going to have a period of 1 here, and you're going to have something over here called the long period transition period, okay? So that's 1. I'm going to color code appropriately. If you've watched a lot of my videos, I like to try to color code things. This is 1, and this is TL, okay? So, so again, the hazard tool can give you both of these for pretty much every site. This 2-period response spectrum is kind of historical. It still can be used today, but we're moving more and more into this multi-period response spectrum, okay? So I'm going to go ahead and label this 2-period response spectrum, all right? Now, again, you can pretty much use either one, but ASCE 722 is really pushing us towards the multi-period response spectrum in that particular direction. And again, I'm going to give you a little bit more information on that. Let's talk about some of these values, T naught and TS, that are affiliated with a 2-period response spectrum, just so we have them, okay? T naught is going to be equal to 0.2 SD1 over SDS, okay? And TS is just SD1 over SDS. And remember, we defined SD1 and SDS in a previous video, okay? Now, depending on where you are falling, which domain you are falling on here, we have different governing equations for SA, all right? So if you're in between a period of 0 and T naught, if you fall within this region right here, let me change colors here, you can calculate SA as, right where I have some more room, SA is equal to SDS times 0.4 plus 0.6 times T over T naught, okay? So basically the equation of this line is this equation right here. And this is all in ASCE 7, so hopefully you're following along with me here. 0.4 plus 0.6 T over T naught, okay? And again, how do we get T naught? Down here, all right? Now, if you're on this horizontal piece right here, guess what? SA just equals SDS, all right? So that's within this domain. You're between T naught and TS, all right? What if you're on this little nonlinear segment right here? Well, we do have an equation for that nonlinear segment. That's going to be SA is equal to SD1 over T. And then if you are, actually this is in between TS and TL. So this actually is the governing equation for this whole nonlinear segment right here, okay? Now, what happens if you fall beyond TL, okay? If your period is beyond TL, well, beyond TL, you're going to have SA is equal to SD1 TL over T squared, all right? Now, what is this T? Well, notice, I've defined T naught and TS, and I've got 1 second here, and I got the long period, transition period, TL here. This comes from this also comes from the ASCE hazard tool and some of the hazard maps within ASCE 7. But what is T, regular T? Well, regular T is the structure period. And guess what we can use most of the time for T? That TA we calculated here, okay? So basically what you're doing is you're using the period of your structure, which we are calculating based on that TA equation, and you enter in to this response spectrum, and you come up wherever you land on that curve, and you extract your spectral acceleration SA. And you do the same kind of thing over here with the multi-period. If you have a particular T value, you just come over and you pull off that SA value. Now, what's the difference between what you're doing with multi-period and 2-period? Not a whole lot of difference in general. It's just in the older 2-period response spectrum, you have these governing equations, and it's like a piecewise function in math, right? You have these governing equations for each one of these pieces, and you would, evaluate the particular equation based on the domain you're on. But for the multi-period response spectrum, you can just visually go right in with T, hit this curve, and read it off directly. So I personally like this kind of move towards multi-period response spectrum because I feel like you can read off spectral accelerations and just get them a lot more straightforward than we used to with the 2-period response spectrum, okay? Now, something else to keep in mind, in general, what ASCE recommends is if you have a period that is below the maximum, below this maximum level on either of these response spectrums. So let's say you have a period down here and you come and hit this early part of the curve. Same thing over here. If you have a low period and you hit this early part of the curve, ASCE recommends that you actually just grab the maximum SA value, okay? So ASCE kind of, effectively says, hey, you can just kind of extend this flat part over and just kind of ignore that first linear part. And then similarly, you can grab this top SA value even if you have a low period over here. So ASCE pretty much tells us to do that as well. So something to keep in mind. What do we do next? Well, next thing we do is we determine the seismic response coefficient, which we call C sub S, using either method 1 or method 2 defined in ASCE 7. Now, this is a little different from the previous version, which was ASCE 716, okay? ASCE 722 has these two methods. ASCE 716 did not have two fully defined methods, okay? At least, not in the way that 722 has further developed them. So this method 1 in ASCE 722 is the preferred method now, okay? So we want to use method 1 when we can, all right? So how do we do it? Well, method 1 says we enter the response spectrum with TA and directly read SA. Okay, I just kind of, talked about that here with the multi-period response spectrum. If TA is less than the period that gives a maximum value of SA, use the maximum value of SA from the response spectrum. Guess what? We just talked about that. That was my little yellow, my yellow markings here. All right. So we do that. We get SA. Okay. We then compute the CS value, which is, again, the seismic response coefficient. How do we do that? Well, the seismic response coefficient, C sub S, is SA divided by R over I, okay? Now, you might be wondering, can we just write this as SA times I over R because you have a fraction in the denominator of another fraction? Sure, yes, mathematically, this is fine, okay? The reason why ASCE 7 writes it this way is because what you're doing, you got to think about what you're doing here, right? You're taking a structural system that has a response modification factor R, and you are adjusting the response modification factor R based on how important the structure is, i.e., its importance factor, which is based on its risk category, okay? So what are you doing? You're saying if you have a more important structure, like a hospital that has an I value of 1.5, we reduce the structure's ductility, okay? And again, R, remember, is a measure of a structure's ductility. All right, so that's the reason why this is expressed in this kind of fraction, all right? But again, mathematically, you can write this. That's fine, all right? Just make sure you know what it means. The next thing we're going to do in method 1 of determining C sub S is compare C sub S, we just calculated it here, against its lower limit, okay? So, again, if you have your ASCE 7 open with me, let's find C sub S lower limit. It's going to be equal to 0.044 SDS times the importance factor, and that has its own limit of 0.01, and this is for sites with S1 less than 0.6. Okay, what the heck did we just write down here? Seems complicated, right? So here's what you got to think. C sub S has a lower limit. You cannot go, your C sub S cannot go lower than the lower limit. That's what we're comparing to. Now, how do we calculate that lower limit? Well, we have this equation, C sub S lower limit, 0.044 SDS times I. Now, the lower limit itself must be bigger than or equal to 0.01 when the site has an S1 less than 0.6. Now, what happens when the site has an S1 bigger than or equal to 0.6? Well, in that case, we say the C sub S lower limit is going to be 0.044 SDS times I bigger than or equal to 0.01 and 0.5 S1 over R over I. And this is for S1 bigger than or equal to 0.6. Okay, so here's how you navigate this. I know this seems like a lot, okay? Here's how you navigate it. You go back to your hazard tool, check what S1 was, okay? If S1 is less than 0.6, then you say, okay, I'm going to calculate my lower limit, 0.044 SDSI, and I'm going to make sure it's bigger than 0.01, okay? What happens if this number becomes like 0.003? Well, then you use 0.01 as the lower limit, okay? Now, when you're getting S1, if S1 is bigger than or equal to 0.6, then you fall into this line item, this category. You have the 0.044 SDSI bigger than or equal to 0.01, and you also have to check this other option for the lower limit, 0.5 S1 over R over I. Now, again, there's a lot of inequalities here. If I were you, I would pause the video, write this down, and really think about it. Make sure you know what you're looking at here, okay? And cross-reference with ASCE 7 document, okay? So that's method 1, okay? Method 2 is what a lot of us are used to, okay? Method 2 is what we're used to from ASCE 716 and the older versions of it. So method 2 says we're going to compute C sub S using SDS. Let's change colors again, okay? Method 2 says, hey, C sub S is going to be equal to SDS over R over I. Okay, so we're snagging SDS directly. Now, if you are doing it this way and you are not directly using the response spectrum, that's okay, but you've got to check an upper limit and a lower limit now, okay? So whereas method 1 only has the lower limit, method 2 has both an upper limit and a lower limit when you are using SDS directly and you're not really reading things directly from the response spectrum. It's fine, but it's a little bit, to me, it's a little bit more hand calculations, okay? So what are the upper limits and lower limits? CS upper limit is going to be SD1 over TA times R over I. And this happens for TA less than or equal to the long period, transition period. And then CS upper limit is going to be SD1 times TL over TA squared times R over I if or for TA is bigger than the long period. Okay. Now, these equations should look kind of familiar. They are pretty much the same thing that I sketched back up here on this 2-period response spectrum in orange. All right. They're all connected together. So let's go back to here. Again, these are the upper limits. You also have lower limits, but guess what? I'm going to put a line here. Lower limbs are the same as method 1, okay? So back on method 1, when we wrote these lower limits, these are the same lower limits for method 2. So basically, method 2 requires you to check an upper limit and a lower limit, whereas method 1, you only have to manually check just the lower limit. And those lower limits are computed the same way for both methods, okay? The final or almost final thing you're going to do in this process is calculate what's called the seismic base shear force, okay? And the way we're going to do that is, let's change colors yet again. What should we go with now? How about purple? We're going to say the seismic base shear force V is equal to that C sub S times capital W, where capital W is the total seismic weight of the structure. So guess what W is equal to? W is equal to the sum of all of those little story weights that we talked about in some other videos, okay? So each level has a seismic weight, okay? W1, W2, W17, however many levels you have. You add all those together, and that's your total seismic weight of the entire structure, okay? Now, one more time, I know I'm kind of jumping around a little bit, but you got to get used to that. The ASCE 7 jumps around all over the place. So back on C sub S, what C sub S do I use? Do I always use the C sub S calculated? Not necessarily, okay? That's why we're checking these upper and lower limits. So remember, if you get a C sub S and then you get a C sub S upper limit and a C sub S lower limit, if the C sub S that you calculate here is smaller than C sub S lower limit, you use C sub S lower limit. If the C sub S you calculated here is bigger than C sub S upper limit, you use C sub S upper limit, okay? And similarly for method 1 that we saw earlier, except you don't have an upper limit for method 1, okay? So the last thing we do in this process that we're interested in is we calculate the story level forces, F sub I, or, I actually probably should call them F sub X to be consistent with ASCE 7. And so F sub X, how about I use purple to be consistent again? Consistency is important. F sub X is going to be CVX times that base shear force. And I have another whole video on discussing CVX, okay? So that's going to be in another video so we can kind of break this content up. So I know this is a lot. It's a lot of kind of cross-referencing, jumping around. It can be a complicated process, especially when you're first learning this. So again, I encourage you to pause the video, have ASCE 7 open while you're going through this process and you're listening and taking notes on this video. Rewind, rewatch, re-listen, okay? After you redo an example of this, it will get smoother for you, okay? And I do have an example video for us as well. So thank you for watching. Don't forget to hit like and subscribe and take a look at all the other videos that I have for your engineering needs. Thanks for watching.